In this lesson, we shall focus on mathematics, MAT3711, real analysis. We shall look at metric spaces, but with a specific focus on past assessments. And we shall look at how past assessments will be solved or need to be solved in this module. And we move forward. Right, we've decided today to take a look at the paper that was written in June 2012. Okay, just a simple paper. And I just picked this up amongst, lots of papers. And this module, therefore, is about real analysis, MA23711, duration is 2 hours. Examination pattern is appointed by department. I said this is a past paper. This examination question paper remains the property of the institution of the university and may not be removed from the examination venue. Okay, obviously this the copy is an old copy. Now, let us look at question 1.
Hello.
Yes, please.
Can we go over the main topics first?
Okay, that's fine. Right. Okay, that's okay. We shall go through the main topics first. Thank you so much. However, before we go through the main topics, because obviously I have prepared the main topics as well. But now, looking at what the paper contains, obviously I'm sure that has been the aim of the inclusion of the paper. So the first question is based on what we call metric spaces, and where do you let XD be a metric space, and you have P a point in X, and also R a real number such that it is positive, and also you have the ball with center P and radius R, the interior point of a set. So you need to be able to define the interior point, a ball, an open subset, a closed subset, the boundary of A. And so I said already, the discussion of a past exam paper is very interesting, but the thing is, it's not so coherent. It moves sometimes, they mix the things up, they take something from a chapter that's in the middle and bring it towards the beginning. So now you need to prove that every ball in XD metric space is open. Obviously, today I planned that we shall also look at questions like the set S be viewed as a subset of R. If you let S be viewed as a subset of R, the real numbers with the usual metric, the usual metric is called the distance metric, and now which is the distance metric between any two numbers, but after the two numbers on the set of real numbers, then you need to be able to find the boundary of S. Okay, those kinds of notions here, and these are kinds of things that obviously we will give so much attention. And then I'm just looking at the paper that was written in 2012. So we have the following, for instance. Right. So, and then question 2. Yeah. Question 2 was just about also metric spaces, but now sequences. You are able to see that question 1 was just about definitions of what you call an open set, a closed set, R, and also the notion of the boundary of a set. Like given the set S, I'm sure today we shall, if time will allow us, to find the boundary of the set S. But obviously we need to first define what a boundary is. Right, and right, so we continue. And right. Okay, we continue. So now we'd look at, question 2. Question 2 is about sequences. Now let XD be a metric space. And then now, right, and then we have that an AN be a sequence in X. Define the following concepts. AN converges, so we're dealing with convergent sequences and Cauchy sequences. Define a Cauchy sequence. And obviously, I mean, the reason for the many definitions is simply because we are very much aware that the Cauchy sequences themselves and the complete metric spaces are concepts you need to learn first. Okay, and so it is very important, therefore, to learn this. So now, as we discuss the material for the course, we must be mindful of the fact that we must be able to actually, in the end, write down the definition of a convergent sequence, define each of the following. AN is convergent. So if it is a sequence in X, it's convergent. Define that. And then now also AN is a Cauchy sequence. Define. Complete metric space, define. Prove that every convergent sequence is a Cauchy sequence. Every convergent sequence is a Cauchy sequence. So prove that every convergent sequence is a what? It's a Cauchy sequence. Okay, so we're gonna prove that. True or false? Every Cauchy sequence is a convergent sequence. Prove or give a counterexample. Okay, so every convergent sequence is a Cauchy sequence. Okay, so now the converse is obviously questionable, and we shall have a discussion about this particular question here. Okay, right, and now Cauchy sequences we have looked at, and so I mean we have sort of gone through the fact that they need to be known and understood, their convergence, and whether every Cauchy sequence is convergent sequence Cauchy. And now consider, for instance, the norm. If you have given the norm where they are with its usual norm, so R2 with its usual norm, so R2 being the two-dimensional space is endowed with the usual norm, the distance norm, and R with the norm equal to the absolute value be the linear operator defined by this. For all these ordered pairs in R2, show that the linear operator is bounded. So you need to be able to show that the linear operator is bounded. So boundedness, and also need to evaluate the actual norm of the linear operator. Because if T, the linear operator, we shall look at how to evaluate the norm here, where that is the distance function. Okay, good. We move on. Compact sets in question 3 would be done after sequences, and also the notion of the norm. In the same question, question 2, we look at the norm as in question 2. Question 3 now is about compact sets. So you need to be able to define compact sets. We'll see another chapter in the course. And the notion of compact set, dense set, is a subset of the metric space. So those are the kinds of things we shall also have a chance to look at. Moreover, we shall show that the union of a finite number of compact sets is a compact set. Yeah. So now the union of a finite number. Okay. So now we speak about countable unions. So now, this is a union. And the minute we use countable union, we actually mean a countable union in the terms of an infinite union. A union of an infinite number of compact sets being compact. Let A be a subset of a metric space X. Show that A is dense in X if and only if the interior of X minus A is empty. Okay, so we shall look at the interior of a set. The union of compact sets. From the definition of a compact set, we look at compact set, dense set, and then dense subset, compact sets, the interior of a set. And therefore, obviously, if one looks at the interior of a set, and now A is dense in X if and only if this is the case. Yeah, I need to prove this one. And now X minus A being the complement of the set A in X. So you look at the interior of the complement. Right, so I mean, we're just looking at the structure of the paper. Also now, in question 3, we're speaking about continuous functions. Use the definition of continuity to show that G is continuous in R, and R2 have the usual metrics. So you let F be a map from the real numbers to real numbers, be continuous function. Define it by this. Show the definition of continuity to show that G is continuous in if R and R2 have the usual metric. Okay, so now I'm going to prove that G is continuous. Right, to show that G is continuous if R and R2 have the usual metrics. 4. Define the Riemann-Stieltje. Define the Riemann-Stieltje integral. So we'll look at the Riemann-Stieltje. Never mind that. Okay. In terms of the upper sum, lower sums, and things. Be sure to define all notation because it has lots of notation. 12 marks. The Riemann-Stieltje. You must be able to know this for exam, and obviously it is expected that there will be questions on the Riemann-Stieltje. integral. Be sure to define all notations used, for example, partition, subinterval, length of subinterval, upper still key integral, lower still key. Yeah, upper still key, lower still key. So look at that. And also you must be able to solve problems. So at this point, you must be able to integrate, like at this point, you need to integrate the function f with respect to d alpha, where alpha itself is a step function. It's a step function, but f is also a step function. You integrate with respect to a step function, different from integrating with respect to x. Okay, so you need to compute the Riemann, the still key, what you call the upper still key integral, the lower still key integral. You need to do those upper still key, lower still key. Okay, good. And then we shall look at the fundamental theorem of calculus. Right. So to say that the fundamental theorem of calculus states that if f is Riemann integrable on a closed interval AB, and there is a differentiable function f on AB such that the derivative is f, then this integral of small f becomes big F. Prove this theorem. So we'll prove the fundamental theorem of calculus. But then, okay, that is the end of the paper. But now, what are we going to do? Because there are things that you'll always find beyond doubt in the exam. And I have lots of things. I think that we're going to actually have a feel of what it means to speak about an exam paper in this module. And I think that, and then we shall revert to the kinds of things that, okay, so we're going to use the dual approach. Okay, so the dual approach will entail covering both the exam and the content, and I feel that that will allow us to, because the module is very long. The truth is, as a matter of fact, there's no way, quite except that if one can, there's no way one needs a whole year to do the course. And so I think that it's very important that we use a double-sided approach that will allow us to say, okay, as much as the exam questions so what we're going to discuss are questions that obviously appear in the material by and large, because the kinds of concepts must be known and understood from the material. For example, there are certain things that I planned we discuss, but let's first have a sense of what it means to speak of the paper. This is the May-June 2012 paper. Okay, some of the questions we can quickly look at here without any doubt. For example, we have not defined the following because we looked at the preliminaries last time, and we let XD be a metric space, P a point in X, and R be a real number, such that R itself is positive. Define the following concept. For instance, the notion of the ball with center R and radius R. Okay, obviously when they mean the ball with center R and radius R, the understanding is it is an open ball, but not so now. So there, in general, there will be two kinds of balls, and obviously at this point, you'd have to say let XD be a metric. Okay, so I know that this is gonna do when we even do the background. So, but if we do it here, then when you get to the background, would be familiar with the definition. So if let XD be a metric space, take A to be a point in the space X, metric space, and R be a real number, with R positive, the ball. The ball with center, okay, the ball with center A. Okay, we can call the center P. So let us take this to be PP. The ball with center P and radius R, right, then radius R, denoted denoted B of PR, right? B of PR. So we're going to just play around with these things. B of PR is the set. Right, it is exactly the following set. And it is B of AR, which is X and X, such that D of XA is less than R. Right. So this is the ball. And so this one is called in open ball. This will be called an open ball. But you see, by the definition here, they meant the open ball. By the open ball, because of the way the material is written. So this one is an open ball with center P and radius R. Okay, so we're going to play around with some of the questions because I know the time might never really suffice to do the whole guide, whatever. We'll see anyway. Right, so, but now the notions that are important is that of an open ball. Okay, but which we just call a ball. So at this point, then you will then say the ball with center P and radius R, and that would be the case. But I must indicate that there are two kinds of balls. So now, this one is not just said to be a ball. So this is enough for the question. But there's something for the question Roman figure 1, but it's something we call the closed ball. Right. So the closed ball is different from this because a ball is either open or closed. Okay. So now we'll add XZ be a metric space. Be a metric space A in X and R positive. The closed ball with center A. Okay, let's call it center P. Let's call it center P. Normally, we normally do it in terms of center A. With center P and radius R denoted B bar of PR. So this one will be a closed ball is the set. So this one would be B bar of AR. Which is the distance of AR okay, so this one it's going to be XP, excuse. And then it's going to be B of PR because of the fact that the center, we called it P and the radius is called R. So, I mean, this will be everything about the two notions of the two kinds of balls we speak about, an open ball and a closed ball. What is the difference? Well, the closed ball includes the boundary, but the open ball has a strict inequality less than. So that is something that you would obviously take note of here as a consequence. And now what we then do, obviously with this, we then say if you have a region like this, you can have a metric space, which is a space. This is the space, metric space. And therefore you can have the center P and the radius R. Right, so you'd have Exactly that. So that would be the center P and the radius R. So by the metric space, one would mean this set metric space. And so if it is the space there, you have inside it P and then R. And then you have the metric space. And then this one is different because now we're speaking about that one where it is this. And this one here is like this. And so this one is going to be the open ball, PR, and this is going to be the closed ball. Right, like that. And therefore, this is going to be the closed ball, which is P bar of PR, XD. So this one, this B bar is the closed ball. Closed ball, and that is open. And I would like us to have a sense of this, obviously, not the notion of what you call, there are points that are interior and exterior. Let us discuss them, but obviously we'll have a chance to reiterate some of these, but let us look at the kinds of points and how we define them in general. But you see, there are too many definitions that right. Okay, there are too many definitions that okay, yeah, there are too many definitions. Okay, yeah, we're moving on, please. Okay, there are too many definitions that ever the exam, this past exam paper is going to cover. So we're going to look at the other definitions, but I just want us to have a sense of this paper here. Because of the cognitive demand of the module, there's certain things you need to just be able to reproduce, like they define the following concepts in the concept of a metric space. What is an interior point in a metric space? And so we would then first, now to state the definition for 1 mark, you need to first define and state that you let XD be a metric space. Right, let XD be a metric space. And X and S, then a point, then a point X in S is called an interior. It's called an interior point of S. If there is a ball, there's a ball B XR such that B, let's look at this one. Such that BXR. Okay, yeah, obviously we're gonna speak about the point A. But let's understand this definition. All right, let's understand this definition. All right, obviously we're speaking about the subset A of the metric space, right? So we are saying let XD be a metric space because that is the definition. So if let XD be a metric space, and we have a point P in R in X. So in the same way here, we can take XD to be a metric space, and also I want us to change this as we learn it normally to A in X, then a point P in X, Okay, yeah. P in X is called an interior point, right? An interior point, right? It is called an interior point of A. So a point, so let X be a metric space and A be a subset of X. Then a point P in X is called an interior point of A if there is a ball, right? And this ball, we can call it, you can change this, but in the context of the question, you'd say center P and radius R. There's a ball of center P and radius R, right? Center P and radius R such that the PR, this particular ball, PR is a subset of A. What does this mean? So that would mean that we have a metric space in which we have, right, and there's a subset A of X. And if this is X, then we have a subset A of X. Right, so if you have a subset, this is XD, the metric space, and we have a subset A of X. Then a point P in X is called an interior point of A if there is a ball such that a ball of center P radius R such that this ball is in A, right? So you have A, and there's this ball, and it's open, and therefore it would follow therefore that this ball here is what? It's of center, okay, it's of center P and radius R, and this ball is entirely contained in the set in A. So here's the ball, center P, radius R, and obviously if this ball with the center P is entirely in the set A, contained in the set A, it's a subset of A, therefore not necessarily proper, in which case it can actually be equal to the set A, because if ever the ball equals the set A, therefore it would be that the ball is an improper subset of A. Okay. Now, what is an open set? So at this point, we'd have defined the notion of an interior point. What is an open subset? Let us define an open subset. What kind of a subset is open? So to define an open subset in the third Roman figure, you let XD be a metric space. Be a metric space and S be a subset of X, then S is said to be open if each point of S is an interior point of S. Let XD be a metric space. And Okay, obviously, in the way that this question has been asked, look at that, it is an open subset of X which has no name in terms of whether it is A or B or S. So we can give this one the name S. So let XD be a metric space. And why is XD a metric space? Well, it is an ordered pair of a set X, which can be the set of real numbers. So X ordinarily becomes a set of real numbers. And now, then we have a distance function. There's something we call we have to discuss this metrics. Okay. So now if one speaks of a metric, this is called the usual metric. Why? Because it is just the distance between two numbers. So the distance between two numbers on the real line is found using this distance function that seeks to take the absolute value of the difference between two numbers. So if you find the difference between two numbers, the difference can at times be negative. But if you take the modulus of that, we're able to find the distance between two numbers on the real line. So you let XD be a metric space. Let XD be a metric space. And S be a subset of X. Then S is said to be open if each point of S is an interior point of S. We repeat. So if we begin with XD as a metric space, and obviously a subset S is a subset of X, then S is said to be open if each point of S is an interior point. Right, so we are defining S to be an open set, and therefore if each point of S is an interior point, an open set is that set such that each of its points is an interior point. What is an interior point of a set? We have defined that one already. Okay, so we need to move on. Now, not all sets are open. Some sets are closed. Certain sets are closed. Right, so we then are able to proceed to the notion of what we call a closed set. Because what then do we do if a set is not open? We give its characterization as what you call a closed set. Right, and I want us to give the actual formal definition of a closed set, and this is it. Right, so we then say a subset. Right, you can start a subset. But yeah, you see, they said just a closed subset of X. A closed subset of X. What is its name? Is it set A, B, or no, nothing like that? So then you would then say that a subset S of a metric space XD is closed if its complement this is it. This is a definition. If its complement is open. If its complement is open. What is a closed subset of a metric space? A closed subset of a metric, so a subset S of a metric space XD is closed if its complement X minus S, this is like X minus S, is open. If the complement of a set is open, then that subset is closed. So how do you know if a subset is closed? You check the complement. If the complement is open, then the subset is closed. That becomes a technique in line with these. This is used as the definition of a closed set. So a definition of a closed set is defined in terms of an open set. Okay, so this is very interesting, but you see there are many characterizations of these things here. But simultaneously, there are more things that we need to learn as we discuss these notions, and as these notions themselves remain very, very important to us, but also they remain very, very close to our hearts. But they are central to our learning here. And there's something we call the boundary of a set. Let's discuss the boundary of a set. Define each of the following concepts, the notion of a boundary. What is the boundary of a set? Given a set A, what is its boundary? So now we're looking at the boundary of A as a set. Right. So now we actually define the following. But to define a boundary, we must define what we call a boundary point. So we let 2 marks because it's long. We must first define a boundary point and then we can define the boundary of a set. But first, we must know what a boundary point is. So let us have this one. Let us have this one. Okay, let's discuss the notion of boundary points and things. Let A be a subset. Right. Let S be a subset. Yes, hello, who am I talking to? Just 1 minute, please. Just 1 minute. Please come again. All right. Just give me a minute. Just give me a minute because I'm in class now. Just give me a minute. Okay. Okay, thanks then. Right, so we continue to do the following. Just 1 second, 1 second, 1 second, 1 second, 1 second. So we let A be a subset. Right, so we let A be a subset. Okay. Okay, we're continuing, please. We'll just we'll respond to the call. Please forgive me. And then now we're continuing because I didn't know whose number that was. Right. So now let A be a subset of a metric space. Subset of a metric space. XZ. A point. P in X is called a boundary point. It's called a boundary point of A. Yeah, boundary point of A. In case. Okay, so you may not really have to give a string of definitions here. In case P, it stands here. In case P is an element of the closure of A, intersection the closure of the complement of A. So P is called a boundary point of A. In case P is an element of the intersection of the closure of A and the complement of A. Okay, this is a smart definition. And you see, the mathematicians look at the fact that if you want to define a boundary point, P is a point that is in the intersection of the closure of A. So if you close the set A, because not all the sets are open. So some sets are, not all the sets are closed. So some sets do not have boundaries. Like this one has no boundary. But if you speak of the boundary point, you must take the closure. Because the open set does not contain its boundary, for example. Well, I mean, does it contain its boundary in the sense of this being what? Being a broken boundary, dashed boundary. So, but now, then we take its closure. We want to define the closure. The closure is a formal definition. If you put a closure like this, then we include the points that are not actually part of the boundary, so we begin including them, and therefore that becomes the closure of A. And intersection, the complement of A. So the complement of A is going to be the region outside, yet now we take its closure. We also close it. So in other words, we take every point. And now if you take the intersection of that, of the exterior and the interior, then not only the interior, but the A with its boundary, the exterior with the boundary of A, and the point surely will be on the boundary there. And therefore, this point P in X is called the boundary point of A, in case P, an element of A, that intersection that is what? P is an element of the closure of A intersection, the closure of the complement of A. Okay, now we are ready to define the most important concept, because here we're defining what we call a boundary point. And they are not asking us to define a boundary point, but before we define a boundary point, first we must define a boundary, I would imagine. That is what is necessary. Now, let us define what we call a boundary. What is a boundary? What do we mean by the boundary of a set A? The boundary of A. The boundary of A denoted the boundary of A is the set of all boundary points the set of all boundary points of A okay, the set of all boundary points of A, that's short. The set of all boundary points of A is the boundary of A. In other words, the boundary of A is the closure of A intersection the closure of X minus A. Okay, so the boundary of A is equal to the closure of A intersection the closure of A complement of X minus A. Okay. So this gives us a sense of what we need to learn. But as said already, this is okay to give us a sense of what we need to know. But again, it is nothing, because it is what? It is something that well, I mean, it's a jump. So we jump from one thing to the next. So by jumping from one thing to the next, it doesn't provide us with the kind of right, doesn't provide us with the kind of understanding we need, I believe. Right. I want us to spend some time and discuss other notions. For example, right. I want us to discuss for 7 marks, part B. So some of these statements would have like multiple ways to prove them, but let us actually discuss the proof of this and how these can be proven, because what you need here, by and large, would not be too many things except what we've learned about what we call a ball, right? So, and now, if you have a ball in a metric space, then you would actually be showing the full that it is open. Okay, and this is a powerful statement. Right. Let us spend some time to try and understand these. Right. So this is a fundamental result, but very, very important. Now, we need to understand where this one comes from. It comes from the notion of an open ball, but also we will spend some time to understand its applications here as well. Right. So let us pause to understand this here. Very strong result. Very strong result. Right. So now, as we understand these results, you'd have the following. Let's look at first the B. So now, to prove this one here, you'd have to first let, well, we're doing part B, you let XD be a metric space. Okay, note that we have not quite yet defined a metric space. Once again, a metric space is a set X endowed with the, what do you call it, distance function, a distance function called a metric. And this distance function is able to, okay, just 1 minute, this guy here. Yes, hello, my dear. Yes, my dear. Yeah, just give me a minute, okay. Okay, thank you. Right, so now what then you would have to do here would be the fact that you let XD be a metric space, and then we will have a couple of concepts and definitions that we need to understand here. Right, just 1 minute. 1 minute is actually I try to in a minute to actually assist this person here who's given me a call twice. Right, and then I will actually just continue just now. With the proof of this, we shall continue the proof, and then we shall look at part C, where we will look at how we actually are able to right. Okay, so in the end, would have the following. Okay, so we continue. We continue just now, please, in a minute, but this person has given me a call 2 times. I'm trying to respond to them quickly. I'm trying to actually assist them so that at least they but now that is gonna take me to just press a button or two. And then we continue. Apologies there. As I'm sure you're thinking about it in terms of what actually do we need to do here to prove this. Okay, obviously to prove this, we begin with a metric space. And if you begin with a metric space, you'd have a situation where, right, we continue, please. Right, let XD be a metric space. And moreover, you'd need and let XD and let B. We need a ball. Right, so we're gonna take and let B PR. And let this one be a ball in XD. Right, so we have this. We have exactly this point here. And so, if this is the case, we use some very interesting but very silly arguments here. And we're going to be using the silly arguments here as a matter of fact. We're going to be using silly arguments here as a matter of fact. Okay, but very interesting arguments which I'll be actually making use of as we move along. So now we're going to be using some arguments as we move along. So now we're going to be using some arguments. Okay, we are going on, please, with this one. We are going on to prove just in a split second. I'm trying to make sure that this person. Okay, just 1 minute. Let me just give this person. I'm trying to help this person who just called me twice, and I'm going to be right back now because this person called me quite unexpectedly. And then we're going to finish this proof. We're going to finish this proof. So let me just give them a call. Okay, 40. Um, let me just give this person a call. Okay, yeah, I'm with you now. Just 1 minute. I'm trying to help this person. I'm so sorry. This person just reached me unexpectedly. Let me see. Let me see. Right. Let me see. Just 1 minute, 1 minute. I'm just I'm trying to help this person out. Get their contact. Let me see. Um, let me see. Just 1 minute, 1 minute. Just let me see. Okay, let me see now. This person is trying to get back to me. Yes, guys. Yeah, you see, your number is not going through, and I tried to call you. Look. Okay, yeah. Now it is the registration number is as follows. Just 1 minute. Okay, I'm just giving you the registration number. It's double K40. For Are you able to see it? Yeah, that's the one. Okay, thanks. Goodbye. Okay, right. So we here and we. Okay, I'm so sorry because I had to try and help this person out, and they just could not wait. In the cold, somehow the weather is quite cold today in the region. Okay, my apologies there. Okay, we're continuing with this. Let's get this one proven. So you let XD be what? Be a metric space and let BPR be a ball in XD. Okay. What is the meaning of these? Right, this implies that this open ball we have defined so many times of center P radius R is non-empty. Well, because we let XD be a metric space and let this one be a ball in XD, at least this ball, if it's so small, it has a center P. If it is so small, there's a center P and some radius. Now, if you assume that this radius is variable, it's a variable radius. All right, it can at least be only the point. Very small radius, then you'd have that it's only the point. Um, so very unlikely there. So it will always contain at least some points there, and it means that for this open ball itself is what, or this ball is not empty, and so at least we have a non-empty state we're dealing with, so we can take some points from it. And because it's not empty, then we then say there exists a y in the x such that there exists a y in the x such that y is an element of what? Of BPR. So we can get a y in x, in the metric space x, such that this y is an element of the ball. Why is it that this y exists? And how sure are we that we can get a y from the ball? Because the ball is non-empty, so at least it contains at least a point. And we call that point y. And this is good news for us because it actually has implications. But one of the implications is therefore that we can be able to find, using the distance function, we can be able to find the distance between our initial point, our initial point P and the point Y. Can be able to find some distance between the point P and also the point Y. And this particular distance is a distance that is smaller than r. Smaller than r. What guarantees that this distance is smaller than r? Well, because of the property of the ball. Because now the ball is defined like we did before. So how do you define the ball? We defined the ball like so. Of center P, radius r, and it contains an x in x such that the distance between x and P is smaller than r. Is smaller than r. Then exists a y in x such that is the case. And this implies that this distance is smaller than r. Okay, because if you find a point y in the ball, then the distance between P and Y is more than R by the definition of an open ball. So surely this would be surely smaller than R. By dint of this, we're able to perform a wonderful construction. And we can then say, let some radius R1 be even smaller. We define a radius that is smaller. So if we then say, by the open ball definition, by definition of a ball, which is an open ball, then the distance is smaller than r between some points. Then we want to find a smaller distance. So we say from the radius r, we subtract this distance. So if you say r minus d of P and Y, it's going to become what? It's going to be positive. It's going to be positive. So that positive distance between these two numbers, we're calling it a new radius R1. Okay? And with this, it is clear. It is very clear. It is clear that the radius R1, for example, is positive. Yeah, we said it's positive because it is R minus dpy, and R minus dpy is bigger than 0, according to this inequality. So indeed, this R1, which is R minus dpy, is bigger than 0. Yeah, it is clear that R1 is positive. R1 is positive because the distance between x and y, I mean the distance between P and Y, it's small. We shall prove that the open ball of center Y and radius R1 is actually an open ball that stays inside the open ball with center P and radius R. We are making the argument that this distance, there are two balls here. This ball that has radius R1, this radius R1 is a smaller radius because it's formed by R minus the D, so it is a smaller radius. So this other radius is much bigger. Okay, it's a much bigger radius. We continue. So in other words, these two balls are not the same, so are not the same size. You have a smaller one and a larger pole. And therefore, this larger pole with a radius, bigger radius r, contains a smaller one. So the smaller one is just inside the bigger one by dint of this. But obviously, you can be say, okay, but these are not purely concentric. They're not purely concentric. But what do we know about this? We know that the y is also in the open ball of center P and radius r. So this one of center P radius r contains the point y, because the point y is in the this one, center P, and this y is in x, such that y is an element of the ball with center P and radius r. So the y is sitting somewhere here. So the y is inside this ball. Now, if we were to form a ball around y, and we formed it with a smaller radius, surely the argument we're making here is that this smaller ball becomes a subset of the BPR, of the larger ball of center P and radius R. Okay, now, if this is true, which we can see, surely it's true by construction of the smaller radius R1, we're able to say let Z be an element of the open ball of center Y and radius R1. The smaller ball, the red one, made the red one here with center Y and radius R1. There's some radius R1. It is the radius is R1 there. Okay, what do we know about this ball here? That small one. That small one, the red one. Okay, we take a point from it and we call the point Z. Let Z be in the smaller radius, smaller ball. Center Y radius R1. Center Y radius R1. Okay, this means what? This means that the distance between Y and Z is smaller than R1. Okay, it's a chain of events, so you need to have a picture. You need to have a picture to sort of discuss these kinds of things here. Discuss these kinds of things. And to understand this, we discuss a space like this. And we call this the metric space, give it the metric space XD. That is the metric space XD, because it is the XD metric space, and we want to show that every open ball in XD is open. So this is the metric space. We can make it rectangular, or it doesn't matter. It's just a set. Okay. Now we're going to have a ball. Oh, it must be like a circle. I agree. It must be like a circle, but this doesn't look like a circle. Okay. For convenience, we are looking at the circles. So let us make it like a circle, like this. And then now this one we call our wonderful one. It has center P, radius R. Okay. And this is it. It is center P and radius R. Okay, let us look at this. So if it is center P and radius R, what is it? Okay, never mind. We're looking at the this BPR. And then we defined a smaller one. Okay, need to make sure we can picture these things a little bit. On this smaller one, we agreed that is the point Y is inside. And then we defined another one, such that this one is small. It is inside there. It is inside this other one. And this red one is of center Y, radius R1. Okay? Okay, we're discussing that. So we have this kind of a setup. We have this kind of a setup. Now we are then saying let Z be a point in this red one. So in the red one, we are taking a point we call Z. And then we're saying the distance between Y and Z is smaller than R1. Well, it is true because both points Y and Z are in the red one, in the red ball, yet the red ball has a radius R1. So the distance between these two is smaller than R1. So indeed, that is true. Next. With that mentioned, okay, we're just trying to prove this statement for 7 marks. Right, we're done with the proof almost. By the triangle inequality. By the triangle. By the triangle inequality. By the triangle inequality. The distance between X and Z is less or equal to the distance between X and Y, the distance Y and Z. Okay. So what is the distance between X and Y? The distance between Y and Z is R1. Okay, let us analyze this one. But now this is equal to the distance between X and Y. Okay, this is a triangle inequality. The distance between X and Z. What is the distance between X and Z? Triangle inequality. So you just introduce a new variable between X and Y. Between X and Z. So that now you have X, Z, and then Y. These are points. And then now you find the distance between X and Z. This one is the distance between X and Y. The distance between Y and Z. And we're then saying the distance between X and Z is generally smaller than the sum of the distances of the other two sides. How true is this? I can imagine that one can say it's always true for any triangle, and hence the triangle inequality. So the distance between X and Z with just 2 points will always be smaller than or equal to the sum of the distances on any other two sides. Okay, so we have that, right? So now the distance between X and Y plus R1. What is R1? What is R1? Now R1 becomes R, which is the biggest one. What is R1? R1 is R minus the distance between X and Y. Let's look at this. So if we then want to find R1, so what is R1? Okay, all right. So we are saying what? Look, okay. R1 is R minus that. I can imagine that obviously that can be evident from this, yeah? It's one of the equations you can use. So if you find R1, we know that is R minus the distance between P and Y. So in particular for us here, I decided to use points. I used P. So this is going to be P with the Y. And then we just introduce the Z. Right, so need this to match everything. So we use the point P. it was like P, center P, radius R. So this is center P. So using that equation where we know that R1 is R minus dpy. R1 is R minus dpy. So that's what we're going to use. So R1 is R minus dpy. So dpy minus dpy is 0, giving us R. So, and this is enough to then say the distance between P and Z is smaller than R. Which means what? Which means Z is an element of the open ball of center P and radius R. And this means, okay, we analyze what this means. So this means that the distance between P and Z is strictly smaller than R. In turn, because of this triangle inequality. But in turn, it means that Z is an element of the open ball of center P and radius R. Yeah, because now Z is actually in this element is in this ball of center P and radius R. So Z is inside because Z is the distance less than R between the distance between Z and P is smaller than R. If the distance between Z and the point P is smaller than R, it means that indeed Z is inside this open ball of center P radius R. Okay, and what is this? What is this? Okay, we are still looking and we are reasoning. But this means that the open ball center Y radius R1 is less or equal to the open ball so now center Y radius R1 is more than the open ball of center P is as a subset. This one is a subset of the open ball of center P radius R. Because the Z, we know this Z is in the BYR1. And now this Z is very interesting set theoretical implications that are cropping up here. Z is in an element of the ball of the center P radius R1. But again, Z, we found that Z is a member of the open ball of center P radius R. It means that this ball BYR1 is a subset of BPR. Okay, if Z is there and this is that. See, in mathematics, we say that if X is an element of a set A and also X, okay, if X is an element of the set A, that's what we say. If X is an element of the set A, implies that X is an element of the set B. This implies that A is a subset of B. If X is an element of A implies that X is an element of B, it means that A is a subset of B. Z is an element of that and implies that Z is an element of this. It means this sets this BYR1 is a subset of BPR. Okay, now, then what is the meaning of this? This is very, very interesting. So we're then saying BYR1 is a subset of BPR. Yeah, we got that BYR1 is a subset of BPR. Thus, B Thus, PR is open, is an open set. Thus, BPR is an open set because it has an open ball inside. If there's an open ball, every point inside has an open ball around it. Therefore, it means that this set itself is open. Because a set that is open, it means that every point inside is sort of an interior point. Now, let's analyze this. So this means, therefore, this is it. That is the conclusion. Therefore, every open ball is an open set. Is an open set. Therefore, every open ball is an open set. Therefore, every open ball is an open set. Now, obviously, this is what we've proven. We've gone through those statements, so you think about it. But also, I mean, we can replay this recording. Now, I want us to look at C. Let S be equal to 1 over n minus 3, such that n is an element of the natural numbers, be viewed as a subset of the real numbers. Let S be 1 over n minus 3, where n is an element of natural numbers. Be viewed as a subset of the real numbers with the usual metric. Find the boundary of S. Found the boundary of S. Find the boundary. Give full justification for your answer. 8 marks. It has much more marks than what we just went through. So there's more pain than what went through. Okay, we're discussing some of these because they are very popular, exam questions. But also, we're going to look at other questions that we're going to look at the background material. Background material. Right. Right. To do with this one here, we then say for Ernie. So we let look at it together and try to make sense of it. What are we supposed to prove here? We need to find the boundary of S. The set S is this one here. You can write like this. You can write like this. It contains 1 over n minus 3 such that n is an element of natural numbers. Find the boundary of S. So to find the boundary of S, we let S be equal to 1 over n minus 3 such that n is an element of the natural numbers. Close brace, be viewed as a subset. Okay, we're yet to discuss some background today. As a subset of the real numbers with the usual metric. The usual metric is the usual distance function. The distance between x and y, usual metric. By usual metric, we mean this distance function, x minus y. Right, so now, with the usual metric, right, with the usual metric, with the usual metric, with the usual metric. Okay, we are going on, please. We are going on with this one. So to prove this one now, we'll then actually begin our proof. We've started the proof, of course, but would say for any, so take a point. Let's call it P. As the introductory part of the question, we're choosing the point P. So for any P, which is a member of S, every neighborhood every neighborhood every neighborhood of P meets S at P, for instance. Okay, when I look at this and what this means. When I look at this and what this means. But before we look at that, we'll say, but this is the case, and also there's certain observations we're able to make, and also meets the complement of S. Right. Since as observed above, every ball, yes, every ball, we saw that in part B, that's why the part B was necessary. So every ball around P contains irrational numbers. Contains irrational numbers. Okay, we analyze this. We are then saying we let S be this given set containing 1 over n minus 3, where n is an element of the naturals, be viewed as a subset of the real numbers with the usual metric. For any point, we pick a point, a random point, P in S. Every neighborhood of P, well, we shall just find a neighborhood, but the neighborhood becomes an open set that contains P. Becomes an open set that contains P. It need not be an open ball, but an open set that contains P is what we call a neighborhood of P. So every neighborhood of P meets S because P is a member of S. So in other words, we have the set S, and then we pick a point P, and then we are then saying every neighborhood of P meets S. At P. For instance, okay, it meets or every neighborhood, every open set, that's by neighborhood we mean every open set that contains P. So every neighborhood of P meets S at P, for instance. At P, for instance. And also meets the complement of S. Right? Since, as observed above here, every ball around P contains irrational numbers. This is it. Every ball around P contains irrational numbers? Well, because this set contains some 1 over n minus 3. If n is 1, what is 1 over 1 minus 3? It's minus 2. 1 minus 3 is a minus 2. And now if p would be minus 2 and you take an open ball around minus 2, on the real line, these are real numbers, minus 2, and then you take an interval on the real numbers. Surely, to the left and the right of minus 2, you'll contain some irrational numbers. You'll find some irrational numbers there. Okay, so that is true that indeed we find some irrational numbers. Thus, S becomes a subset of the boundary of S. This is very interesting. So we're effective in saying we take a point in S. A point in S will be such that every ball around P, if P is minus 2, yeah, call this P. Every ball around P contains irrational numbers. So in other words, every P in S, for any P in S, every neighborhood of P meets S at P meets S at P, for instance, yeah, meets S at P, for instance. And also, every neighborhood of P, since as observed above, every ball around P contains irrational numbers. Every open ball around P contains irrational numbers. And therefore, this means that the S is a subset of the boundary of S. Okay, I'm sure we shall understand this a little bit more. We shall elaborate on this. Let us say the following. Next. Let us say the following. Next. So next. Every neighborhood, every neighborhood of 2 contains 2. Which is not in S. Which is not in S. Next, every neighborhood of 2 contains 2. Which is not in S. Why is 2 not in S? Because there's no natural number you can pick here, such that 1 over that number minus 3 is going to give 2. If you take 1 minus 3, it's minus 2, and the rest of the numbers will not give 2. So next, every neighborhood of 2 contains 2, which is not in S. And also contains 2 minus 1 over, I want to say here, contains, here I want to say every neighborhood of 3. Or I can say every neighborhood of -3, right? Every neighborhood of -3, that's what I want to say, contains -3. And -3 is not in S, that's what I want to say. And also, right, and also, contains 1 over n minus 3 for some for some m 1 over m minus 3 for some m in the naturals, yeah. Okay. Since 1 over m minus 3, 1 over m minus 3, right, since 1 over m minus 3, right, since 1 over m minus 3, let's finish it off here. Right, so want to say since 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 okay, let's continue, please. And here we said since, but this since I would like us to remove this one and continue on the other side to say since. Right. Since 1 over m minus 3, changing the n to m, let me see what I've said here. For some m in n, okay, I wanted to say since it was for some m in, let's switch back to n. Let's switch back to n. Since 1 over n minus 3, which is this, converges to minus 3 as n approaches infinity. And this shows that this shows that 2 is an element of the boundary. Yeah, okay. This shows that minus 3, that's what I mean. This shows that minus 3 is an element of the boundary of S. Full stop. Consequently, the set S union minus 3 is a subset of the boundary of S. Now note that if Q is not an element of S note that if Q is not an element of S union minus 3, then we can find epsilon positive such that Q minus epsilon, Q plus epsilon does not contain an element of S. We shall discuss this, please. But however, this goes to show, so this shows that if Q is not in the union, then Q is not in the boundary of S. Shall discuss this. Consequently, the boundary of S is a subset of S union and hence the boundary is S union minus 3. Find the boundary. So this is the boundary of S. Is the set S union minus 3. Okay, now let us go through this. Since 1 over n minus 3 approaches minus 3 as n approaches infinity. Because if n approaches infinity, then 1 over infinity becomes 0, giving us minus 3. This shows that minus 3 is an element of the boundary of S. But as a consequence, consequently, it means, therefore, we can take S now and include the minus 3. And therefore, we're going to find that S together with minus 3 is a subset of the boundary of S, because it is just S with minus 3, and potentially the boundary of S has more points than just the additional minus 3 to the set S. And therefore, it makes sense to therefore say the S union, the point minus 3, the set that contains only 1 point, is a subset of the boundary. Now, note that if okay, let's continue, please. We're analyzing this. Consequently, once again, we're saying the set S union, the singleton set that contains minus 3 is a subset of the boundary. We understand that the boundary of S is S together with its boundary points. Right. So the boundary, this is like 1 point, boundary point, and therefore the potentially more, and therefore S union with 1 boundary point is a subset of the set S with all its boundary points, which is the boundary of S. Boundary of S is the set S with all the boundary points. So it's bigger than just an additional one boundary point to S. Now, note that if Q is not in this set, we are just now coming up with Q. And we're then saying Q is not a member, is not an element of this set, then we can find an epsilon that is positive. we can find an epsilon that is positive. Such that we can find an epsilon that is positive. Such that the Q minus epsilon, the interval, open interval, an open interval which is subset of R, the real numbers, Q minus epsilon and then Q minus epsilon. And what does this mean? We have Q here, Q minus epsilon, Q plus epsilon. And then we can form an interval there. The Q minus epsilon is a number that is there. Q plus epsilon is a number that is there. Q is there. So we're then saying, if Q is not in the set S union minus 3, we can find an epsilon positive such that we can form this interval. So that this interval does not contain an element of S. 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 Okay. This interval does not contain an element of S because Q is not in S union the boundary point. This shows that if Q is not in S union minus 3, then Q is not in the boundary of S. By contraposition, Q is not in the union, then Q is not in the boundary of S. Consequently, by contraposition, we learn this in mathematical logic. That we did that in 2613. That P implies Q is logically equivalent. Okay, so we then say, yeah, that never mind, the same thing. Not Q implies not P. P plus Q implies is logical equivalent. Not Q implies not P. P implies Q implies that it would rather is logical equivalent to not Q implies. This is called the contrapositive. And this one is called the contrapositive. Contrapositive. Okay. Right. Okay. Yeah. So contrapositive of P plus Q is not Q implies not P. Now, it comes here. So we are then saying this shows that if Q is not in the set, then Q not in the set, then it's not in the boundary. Not Q implies not P means you start from the end. It means the boundary is a subset of this. It means the boundary is a subset of the union, and hence the boundary equals the union. How do we know the boundary then as a consequence equals the union? Because it is because of the two understandings. We first had okay, S is a subset of the boundary. S is a subset of the boundary. S is a subset of the boundary, but the boundary is a subset of S. Union that. But also this one. This one. Okay, we continue, please. We continue. S union the boundary point is a subset of the boundary. Conversely, the boundary is a subset of the union, and hence The boundary equals the union. Okay, so we have proven this one. Let us see some other problems here that we can do. I would like us to spend some time also discussing some of these things that remain very important, but there are certain notions that we need to learn. We're familiarizing ourselves with these notions, but as said already, we're yet to cover enough background, but we're going to be using this kind of a blended approach. And this blended approach will have to combine, because the truth is this module is so dense. Okay, it's full of theory. Because it is full of theory, what we need to do is to do theory practice, theory and practice, theory and practice. And then it will make more sense that way, because we can't just be looking at only the applications, because of then it will just be a waste of time. So we start as follows. Okay, now first we want to define each of the following concepts. If you let X be a metric space in question 2 and AN be a sequence in X, define each of the following concepts. Now, at this point, if you then say the sequence AN converges in X, define it. Let XN be a sequence. Be a sequence in a metric space be a sequence in a metric space XT, and let P, usual to use P here, P be an element of big X. We say the sequence converges okay, yeah, let's call this sequence AN, please. Right, let's call this sequence AN. Let AN be a sequence in a metric space XD, and let P be an element of X. We say that the sequence converges. We say that the sequence, yeah, I can just say that the sequence converges to P if for every epsilon positive there exists a natural number n0 such that the distance xn and a, rather, the distance an and p, the distance between an and p is less than epsilon whenever n itself is greater or equal to n sub 0. It's greater or equal to n sub 0. Okay. Right. Moreover, so this is it. But now we can say in red. In this case, we say P is the limit. Is the limit of the sequence. We use the notation. So the answer is the blue one. We use the notation. We use the notation AN converges to P, or the limit of AN is equal to P. It's equal to P, yeah? Because you said it converges to P. So this AN converges to P. So now we use that notation. Is equal to P. Or we use the notation. There are fun notations like or. To write clearly here, you have the limit. This will be ANN. Once we write the ANN, we mean n approaches infinity to indicate that the sequence converges to P. Converges to P. Okay, the blue one is the answer to this question. Let AN be a sequence in a metric space XT and let P be a point in X. We say the sequence converges to P if for every epsilon positive there exists a natural number n0 such that the distance between AN and P is less than epsilon whenever this n increases without bound, and whenever n approaches infinity, we say that n is bigger than a fixed natural number n0, and when this happens, we say therefore an converges to P, and therefore we then say it converges in X. Okay, let us indulge and discuss some of the very, very interesting but very fascinating, but also very important notions of what we call Cauchy sequences. What kind of sequence are Cauchy? Because this one is a sequence. AN is a sequence, but there are some sequences that have a specific characterization, and they're characterized as Cauchy sequences. Let's look at this second point. And we note that a sequence AN in a metric space XD is called a Cauchy sequence. It's called a Cauchy sequence if for every epsilon positive there exists a natural number n sub 0 such that um if mn N0, then you have xm, which is less than epsilon. Okay, we continue, please. The sequence AN in a metric space XD is called a Cauchy sequence. If for every epsilon positive, there exists a natural number N0, such that or N sub 0, such that if M and N are bigger or equal to N0, what does it mean M and N are bigger than N0? It means this M and N like approach infinity. Then the distance between the xm and xn, when m and n approach infinity, then this distance between them is smaller than epsilon. And therefore, this sequence is called a Cauchy sequence. So it can be stated in many ways. In terms of the usual metric, you can then say, obviously, the distance between xm and xn, but obviously, see, this is not just the usual metric. It's there are many metrics we study. There are many distance functions. So, but you can then say, for instance, xm and then xn is the distance between xm minus xn, and therefore this distance is less than epsilon. Okay, so whenever m and n, okay, m and n approach infinity, m and n approach infinity. So to say that, we say, instead of saying m and n approach infinity, we say if for every epsilon positive, there exists a natural number n0. Such that if m and n are positive, such that if m and n are greater or equal to n0, then the distance between xm and xn is smaller than epsilon. It means that these xm and xn, they sort of converge to the same limit. Right. They sort of converge to the same limit. They sort of converge to the same limit. Okay. Now, this is what we have. Now, this is then very important because we have defined a Cauchy sequence. A sequence AN. So now you repeat these because you need to learn them in memory. But again, we are here to do most of the background that pertains to these things, so that there are more definitions that we've jumped to actually just look at only these. So it's not that obviously one is supposed to only learn these. Let's define a complete metric space. But now the complete metric space is defined in terms of what we call Cauchy sequences. And now a sequence AN, for one more time, in a metric space is called Cauchy. It's called the Cauchy sequence if for every epsilon positive, there exists a natural number n0, so that if m and n are greater or equal to n0, then the distance between xm and xn is less than epsilon. Let's define a complete metric space. A metric space. So we're looking at Roman figure 3. A metric space. A metric space XD is Cauchy, or rather is said to be complete. Said to be complete is said to be complete if for every, or rather if every Cauchy sequence, if every Cauchy sequence in X converges, to a point of X. A metric space XD is said to be complete. When is it complete? A metric space if every Cauchy sequence in X converges to a point in X. If every Cauchy sequence in X converges to a point in X, then we have a complete metric space. And this is actually what we have got. And that's what we've discussed about the complete metric spaces. What is the complete metric space? So we note that to define a complete metric space, we must first define Cauchy sequences. But now a metric space XD is said to be complete if every Cauchy sequence in X converges to a point that occurs in X. And therefore, we have a Cauchy sequence. Next point. Okay, next, we shall prove that every convergence sequence is Cauchy. Right. Right. Right, 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 right. Right, right, right. Right. I think that we're gonna do these next time. It's okay. I think we're gonna do this next time. Okay, we're gonna finish. We're gonna actually after discuss the paper also in detail. This was the paper we looked at, and I'm sure that it makes a bit of sense. So what you need to do is you need to think about this paper. Make sure that you understand this paper very, very well. Because if you understand this paper, then you'll have a sense of what's happening. But I mean, we're yet to look at more other notions that remain very elementary and that we need to sort of cover and understand. But I think that, okay, there are many things I've prepared that are background material to this. In particular, we need to spend time a little bit on the basics of this. The background sections like what a metric is, what a metric space is, not only definitions, but solving problems in the context of showing that a function is a distance function. A given function is what? It's called a metric. So showing that a given function is a metric, which is different from metric. Okay, because now this metric means distance. And this metric means with the M means grade 12, at least in the South African context. Okay, so yeah, we're gonna be actually we need to solve problems here and go through the axioms, those axioms of a metric, etc., etc. The triangular equality, non-negativity, and so on. And we need to make sure that we can prove all the symmetry and other conditions that are necessary to show that a given function is a distance function and therefore a metric. All right, I must thank you for joining us. It was awesome having this discussion. And I know very well we can always go on and on and on. And my wish is that we continue, but I know very well that on average we have done something for today. But in our meeting next time, we shall cover we shall use a blended approach, in which case we shall have a sense of both. I will always think about how best to do that. But one of the most important things will be to finish this paper and also cover some background in our next meeting. I think that is immediate. Right. So, any question, anything, I don't know, whatever you would wish to ask. Because I just, today's approach was, doesn't matter, was motivated by the fact that I just thought it would be best to do a paper because you suggested we do a paper. But also a paper allows us to like quickly go through the things, at least have a sense of what's happening and what needs to be done in the end. Than having to go through every concept. The truth is, it's just lots of things to cover. And but we shall use that blended approach, both papers, past papers, together with the content to be learned from the study guide. I'm sure that with that, then we'll have a fair understanding of what must be known. All right. Ahmad, thank you for joining us. Also, I'm having this discussion. Right. We shall make this recording available so that you can just watch a little bit and Yeah, learning this course is about repeating. The question is, how does one learn a definition? How do we learn a definition? The way to learn a definition is if you repeat. You say it again and again, like a song. How do you learn a song? To sing a song, even when you were in primary school, you had to sing the song and repeat the song and repeat the song. Practice. Even the choir people, they go and sing until they know how to sing properly and so on. And I'm sure that learning definitions is not different. I must thank you for joining us. Until next time. Yeah, I think you'll take care. Obviously, you said Fridays, so I'm assuming Fridays ideal. But now Friday, then the other Friday, then we can take the remaining part of this paper in some background. We'll see how I can expedite that to make sure that at least we can cover much of the paper and some notes as well. Right. Thank you so much for joining us, but I'm going to make the recording available. Obviously, we shall discuss then, but yeah, I know that we are meeting on Fridays. But in principle, then Fridays must be 12. The 12th has been okay, but just that somebody came up and just suggested today that something had to be done. So that's the reason why we missed. That is the reason why we changed the time. So it's something that obviously you need to think about.